Hello and welcome! In this lecture we're going to begin building our grid system according to our design. Okay, so let's get to work on the grid system. First let's make our script. So on the scripts folder, create a new C# script, call it the grid system, and let's open it. Now for this one, we're actually going to make it a standard C# class. So we are not going to extend MonoBehavior. So go ahead and remove this. Now the reason why we're doing that is because we want to be able to use the constructor to create our grid system. Our grid is going to require some parameters for initialization, so the constructor makes sense. And if you extend MonoBehavior, you cannot use a constructor. So that is why we removed it. So over here we can now make a constructor. So make public grid system. Now if this is the first time you're hearing about a constructor, like maybe you've always used MonoBehavior and you never worked with a regular C# object, if so, here's a quick explanation. Basically, the constructor is kind of like the name implies, the way that you construct an object or an instance of a certain class. The syntax for the constructor is kind of like a function. So first we have the accessor, so something like public, private, or any of those. But then, unlike the function, you have no return type. That is because the job of the constructor is to construct the object, so the return value is essentially the object itself. And for the name of the constructor is exactly the same as the class name. Finally, you can optionally either add some parameters or none. So the constructor is what you use to create an object. Basically, when you use MonoBehavior, you are letting Unity construct that object for you, but if you make a class that does not inherit from MonoBehavior, then you can use the constructor yourself. Then how we use the constructor is with the new keyword, which we're going to see in a bit, and in doing so, it's going to essentially run this code. Now, like I said for design, we're going to need a width and height. So up here, let's make a private. And for the size of those, let's make them ints. We don't want decimals in our grid system. We don't want to have fractions of a grid position. So let's define a width and another private int for the height. Then let's receive them in the constructor. So an int for the width and an int for the height. Then just set this dot width equals this and this dot height. Okay, we have our basic fields. And just with this, let's actually add some sort of visual. For that, we're going to use debug.drawLine. This is a great helper function for drawing a line. We can draw a simple line in our grid position to see it. And let's do that inside 2for, so let's cycle through the entire grid. So for starting with an int x, starting off at 0, x under width, x++. Then inside, let's cycle through the z. Again, remember what I mentioned in the design lecture. This is a z because we want the grid to be placed along the xz axis. So technically, here you would compare z with the length, but personally I think the word height makes more sense in this case, so that's why I'm using z and height. And now here, let's call our debug.drawLine. So for this one, we need a start and an end vector. This is a vector3 for the world position, so let's make a function to convert a grid position onto a world position. So up here, let's make it. And let's make it public since we're going to need this outside of this class. So a vector3, call it getWorldPosition. Receive an int for the x, an int for the z. And then here it's very simple. Let's just instruct a vector. We're going to handle the cell size in a bit. So just return a new vector3, put the x, 0, and the z. Okay, we have our world position, so let's use it up here with this x and this z. Then for the end vector, let's just add a tiny offset. We really just wanted to see a bunch of small dashes. So plus, let's use vector3.right, multiplied by some small amount. Again, just testing visuals. Then for the color, let's go with color.white. And finally for the duration, this is how long the line should be visible for. Now if you set it to 0, then it lasts just a single frame. In this case, we want to last it a bit longer than that, so let's just put something like 1000. Again, these are just debug visuals. We're going to get rid of this in a bit. But with this, it should be enough for testing. And again, we made this a regular C# class, so no MonoBehavior. So in order to test this, we need some sort of testing script. So back in the editor, let's make a script to do a bunch of testing. So let's create a new C# script, call it just testing. Let's make a game object to run it, call it testing, attach the script, reset transform, and open it. Now here, let's first make a simple private void start. And on start, let's just create a new grid system, let's say with a width and height of 10. Okay, so that's pretty much it. Let's test. Here we are, and actually by default you probably don't see anything. That is because in order to see gizmos on the game view, on the top right corner we've got a button for gizmos, so we need to enable this, and when we do, yep, we do see all of our dashes. We can now pause the scene to go back into scene view, and in scene view move around with the camera, and we can see all the dashes. Let's actually get rid of the floor so we can definitely see them. And yep, here are all the grid positions. We've got 0, 0 in here, 1, 0 in here, 1, 1 in here, and so on. Okay, so with this our basic grid is already set up. Now let's implement the cell size. So back on the grid system script, on the constructor, let's receive another one. This one, let's make it a float for the cell size. And let's also store it. Now how we use it is very simple. We just need to use it when handling the grid to world conversion. So down here, when we are creating a world position, we just need to do some simple math. So literally just create the vector and then multiply by the cell size. That's really it. So let's go into our testing script, and over here let's pass in a certain cell size and, like I said, 2 units. Okay, so let's test like this. Here we are, and yep, the grids are now 2 units apart instead of just 1. So again, if we pause, and we can actually verify that they are in the correct position. So on the hierarchy, let's create an empty game object. Let's put it on a Y of 0 so we can move it around, and we can see this one right there on the corner. Yep, it's on position 0, 0. And this one next to it, yep, it's on 2, 0. And that one in there, it's on 2, 2. So this one is actually grid position 1, 1, but it is in world position 2, 2. All right, awesome. Now let's do the opposite conversion. Let's convert a world position back into a grid position. So in the grid system script, let's make a public. Then for the type, let's see that in a bit, and we're going to call this get grid position. Now for the type, like I mentioned in design, let's create a proper grid position type. We can either create it directly down here on this file, or we can make a separate file for it. Either way works, but let's make a new file. So in the editor, let's create a brand new C# script. Call this grid position and open it. Now here, let's get rid of pretty much all of the default code. This one is going to be pretty simple. So let's make it a public, and we're going to make this a struct and call it grid position. Then inside it, we just have a public int for the X and a public int for the Z. And just as a helper function, let's also make the constructor. So a public grid position, let's receive an int for the X, int for the Z, and we just assign them. Okay, that's it. Now here, notice how I made this a struct and not a class. Basically, the main difference between those two is a struct is a value type, whereas a class is a reference type. That means that when you work with classes, you're working with a reference, but when working with structs, you're passing in copies of the values. Even if this is the first time you're hearing about structs, you've certainly used them already. In fact, if we go into the vector3 that is built into Unity, if we look, yep, this is indeed a struct. Whereas if we have, for example, a sprite render class, this one, as you can see, yep, it is a class. So if you use a sprite render as a function parameter, you get a reference to that object. Then in that function, any change that you'll make will be applicable to that same original object. Whereas if you pass in a vector3 as a parameter, instead you receive a copy. So you can modify the X, Y, and Z, and the original data will remain unchanged. What we want here is really for the grid position to work pretty much exactly the same way as a vector3. So when we pass in a grid position as some argument on a function, we want to pass in a copy of the values and not a reference to the same object. So like I said, basically we want this to work exactly like a vector3 rather than something like a sprite render. So that is why we're making this a struct. Also, since here I'm talking about vector3, let me again mention why we're building our own custom struct instead of using the built-in vector2 int. This one does indeed work with ints, which is one of our requirements, so we could use this. But we defined our grid logic using the xz axes, whereas here vector2 int is built with xy in mind. So technically we could make it work and just convert the x to y back and forth, but that would add quite a lot of needless complexity. Also, having a proper name like grid position will make things so much easier to understand. So because of those reasons, that is why we're using a custom struct grid position instead of the built-in vector2 int. And for testing, let's actually do one more thing. Let's create a proper text representation for this struct. Now before we can do that, let's actually comment out this function so we don't have an error so the code actually compiles. So just comment that out. And to see why we need what we're going to build, let's actually go into testing. And over here, let's do just a simple debug.log and create a new grid position. Grid position, say 5, 7. Okay, so we're doing a log on this position. Let's see what this says. Again, make sure you comment out the incomplete function so the code actually compiles. And yep, here we have our log, and it is saying that this is a grid position, but that's not really very useful. We don't know what values are stored in this grid position. We really want to see the x and the z. So on the grid position definition, over here we can actually add a normal C# thing. Basically, all C# objects have a function called toString. That is actually what debug.log calls automatically. It calls toString on any C# object. And with that, we can actually override it. So we can do public override, and we're going to override the toString function. This one, as you can see, returns a string, and it's called toString. Now we can override it to get some custom behavior. So in our case, like I said, we want to see the internals, the x and the z. So over here, instead of returning the base toString, let's return x, and then print out the x, and then the z. Okay, that should do it. Also, by the way, if you find this syntax a bit confusing with all of these pluses, these quotes, and so on, you can also use the C# string interpolation. So you just add a $sign here, then you just need to add one series of quotes, and inside you can add curly braces, put the x, then some text, and put the z. So this is exactly the same thing that we had previously. Okay, so let's test this. And yep, there it is. Now instead of just saying grid position, now we can see our actual values. So this is going to be very useful for testing. Okay, so our nice grid position structure is correctly defined. Let's go back into our grid system. Let's get rid of these comments. And for this function, we're going to return a grid position. Then as a parameter, let's receive a vector3 for the world position. And then here we just return. We create a new grid position. And now we need to do the opposite conversion that we did here. So that is actually quite simple. We just take the world position, we grab the x, and instead of multiplying, then we divide by cell size. Then same thing for the z, just grab the world position z and divide it. And now here we see an error because the vector3 works with floats, whereas we need ints. So simple solution, just use methf.round to int. So it rounds all of these into an int. Alright, so this should be working. Now for testing, let's go into our testing script and let's test it with the mouse position. So let's make a quick private void update. And on update, let's do a debug.log. Let's go into the grid system. So let's actually store a reference for it. Private grid system for the grid system. And over here, when we construct, let's set it. Then down here, we can go into the grid system. And we call get grid position, and then for the world position, let's go into our mouse world class and get the mouse position. Alright, so this should be printing the grid position right under the mouse. So let's test. Okay, here we are, and yep, we can already see it working. So if I put the mouse in here, I'm on grid position 0, 0. If I move it here, 1, 0, 2, 0, and so on. So wherever I place the mouse, I am correctly converting a world position back into a grid position. Alright, awesome. So all of the conversions are working perfectly. We can convert from a grid position onto a world position and convert from a world position back onto a grid position. So in this lecture, we created the base grid system with a certain width and height. We made the grid position and handled conversion to and from grid and world position. Now in the next lecture, let's begin working on creating an actual grid object.